Mr. True, in this math lesson, based on the definition that I is equal to the square root of -1, we're going to do 3 examples, the last one 2 different ways, so really 4 examples, if you will, of evaluating expressions that involve high powers of I. We're going to start off with the basics. We're going to run through the I to the first, second, third, and fourth, fifth, sixth, seventh, and finally the 8th power to let you see how this develops with low powers, and the fact there is some repetition pattern that involves with the pattern of I. We're then going to look at our first example, which is fairly straightforward. We're going to have I to the 5th, 7th, and to the 22nd power. But then we're going to look at another expression where we have I being raised all the way up to like the 1500th power. And our last example is also going to involve some very high powers, and there's going to be 2 ways of evaluating this expression. You can use the pattern that evolves as you look at ever-increasing powers of I, or evaluate the expression maybe using a partial sums formula for your geometric and arithmetic series. So we'll be looking at a review of that concept if you've already learned it in your textbook. My students have, with the textbook I'm teaching out of, I believe. Yeah, well, at any rate. So, evaluating expressions with power of I. Well, we have that I is equal to the square root of -1 by definition. It is basically part of your complex numbers where there is a real term and an imaginary term. If we say that I is equal to, or we're told that by definition I is equal to the square root of -1, then I squared is equal to, well, the square root of -1 times the square root of -1. And we know that if we square a square root, those are inverse math operations, and you just get what's on the inside. So I squared is equal to -1. We have I to the third, which now that I know what I to the first and I squared is, I can say that I to the third, using my properties of exponents, is equal to I times I squared. Well, we just looked at how I squared is equal to the square root of -1 times the square root of -1. Thus it is -1, so I to the third power is negative I. Now if we look at I to the fourth, I can write that as I squared times I squared, right? When you multiply like bases, you add those exponents. So yeah, this is an equivalent statement. And I squared is equal to -1, so we're looking at -1 times -1, which is equal to 1. So what we're looking at basically is we have, I squared is -1, I to the third is negative I, and I to the fourth goes back to 1. So if we say what's I to the 5th power, well then that's I to the 4th times I. That's going to be equal to 1 times I, which is just equal to I. So I to the 5th is equal to just I. If we have I to the 6th, well then that's going to be I to the 4th, and I'm going to focus on this I to the 4th power because I to the 4th is just simply equal to 1, times I squared. And what I want to look at here is basically if I to the 4th is equal to 1, then I to the 6th is equal to I squared, which we have here shown is equal to -1. And I want to focus on this relationship here, that I to the 5th is basically the same as I to the 1st. I to the 6th is the same as I to the 2nd power. If we look at I to the 7th, well then that's I to the 4th times I to the 3rd. So I to the 7th is the same as I to the 3rd, which means that we're going to be looking at just simply negative I. And then I to the 8th is equal to I to the 4th times I to the 4th, which is equal to 1 times 1, which is equal to 1. Now, we're going to use this cyclical property here, basically, or pattern. The values of the powers that you get for I, -1, I square, negative I and 1 just start to repeat. So I, -1, negative I, 1, I, -1, negative I, 1, or the fact that we've got 1, 2, these are the same, I squared and I to the 6th. I to the 3rd is the same as I to the 7th. We have I to the 4th is the same as I to the 8th, which is I to the 4th is 1 and I to the 8th is 1, or basically I to the 4th. Every rotation of 4, you just start to repeat this pattern. So, okay, so our first example we have here, which we have I to the 5th power, which is equal to I to the 4th raised to the 1st power times I. We have I to the 7th, which is equal to I to the 4th raised to the 1st power. And then we've got another I to the 3rd, kind of basically just rewriting what that I've already run through here with our powers of I to the 1st through the 8th power. And I'm doing a little bit something different here with the parentheses and the I to the 4th raised to some power. And here is where that comes in. On our 3rd term, we have plus, and this isn't necessarily a total requirement, I'm just trying to explain the mathematics of what's going on. I'm focusing on I to the 4th for two ways of justifying this. We have, the best way really is to think of like I to the 4th is equal to 1. So this is just going to be 1 times whatever part I complete, or we can think about it again as that cycles. How many cycles of 4 do we have in whatever high power that we have going on here? So with our 22, we have, well, 22 divided by 4 is equal to 5. So I can say that we have I to the 4th then raised to the 5th power, because of course when you have stacked exponents, you can multiply those, and this is equivalent to I to the 20th power. But then we have that remainder of 2. So now we have I to the 20th power times I squared. And of course we just have 1 to the 1st and 1 to the 1st and 1 raised to the 5th power. So we're looking at I to the 5th times I to the 7th plus, I said times, plus I to the 22nd is equivalent to just simply I plus I to the 3rd plus I squared, bringing this high powers down to the powers of 1, 2, 3, and maybe possibly 4, except maybe not, because then you wouldn't have a remainder if it was evenly divided by 4, if your high power was evenly divided by 4. But we have I to the 3rd is negative I, and then we have I squared, which is equal to negative 1. Well, now you can start, now that we've dealt with the powers of I, and even got from those high powers down to powers of 1, 2, 3, and 4, which is equal to 1, I to the 4th is equal to 1, now we just deal with these like we're dealing with variables. We have 1I plus negative 1I. We're just going to add those like basically as if they're like terms, because they are. Those are going to cancel out, adding up to be 0, and our final answer is equal to negative 1. So all of this mess is simply, just negative 1. Our second example coming up right now. For our second example, and now things are getting interesting. We have 5 times I to the 1500th power minus 2 times I to the 1501 power over 3 times I to the power of 1502 plus 4 times I to the 1503. And it's not really uncommon with these questions of just evaluating these expressions. They're really just forcing you to recognize this pattern that you have with high powers of I, how they cycle every 4 repetitions, or every 4 terms basically, or 4 powers, that they give you these powers really close to each other, because we're not trying to completely torture you. We're just saying, hey, look at dividing one of these very large numbers by 4, see what the remainder is, and then you can just adjust that remainder by 1 to set up the remaining terms that are in this single term. 2 terms in the numerator and 2 terms in the denominator. So we're dividing by 4, and I know that some odd number is not going to divide evenly by 4, and we don't really need an even division, but we're going to pick on the 1500. And so we're going to do 1500. We're going to divide that by 4. We've got, 3 4s that go into 15, giving you 12. We're going to subtract and get 30. Now we got what, 7 4s that go into 30. That's going to be 28. Subtract again, we get 2. Bring down the 0, we got 20. And yeah, okay, so 4 divided by, or how many 4s, excuse me, go into 20? That's going to be 5. So actually, 4 divides evenly into 1500 perfectly. So we have a remainder of 0. 4 is a factor of 1500. That's going to allow me to write 5 times I to the 4th to the 375th power. And yes, this is just going to be 1, but I'm just showing all my work here. We got minus 2, we have I. Now, of course, 1501. Well, if 4 goes into 1500 evenly, it's going to go into 1501 the same number of times, except with the remainder of 1. So we're looking at I to the 4th being raised to the 375th power times another I. Yeah, that's how we're going to deal with the remainder. There's a remainder of 1. So let's expand this out. 4 times 375 is 1500 plus another 1 gives you that power of 1501. And continuing that on, in the denominator we have 3 times I to the 4th, again raised to the 375th power because all these exponents are so close together. But now it's 1502, giving us a remainder of 2. And with our last term here, we don't have a 2. We have plus 4. We have I to the 4th. I to the 4th is 1. How many cycles of 4 do we have? That's 375. And that's with the remainder of 3, so times I to the 3rd. So I'm just making this expression look different. Each of these powers of 4 raised to some other power, 1 to any power, is simply equal to 1. So all these are not necessarily canceling out, but it's a multiplication of 1. So that's your multiplicative identity. It doesn't really do anything. So we're looking at 5 minus 2i over 3i squared plus 4i to the 3rd, but just to kind of speed this up a little bit, I have to simplify this anyway. So we have I to the 3rd. Okay, well, I to the 3rd power is negative I, and we've got I squared, which is equal to negative 1. So 3 times negative 1 is negative 3. In the numerator we have 5 minus 2i, so we're close to finishing the evaluation of this expression, but we have a fraction, it's got a binomial in the denominator, and part of that binomial has an I in it. Basically, we have a complex number in the denominator of our fraction here, so we're going to rationalize, if you will. We're going to get this I, this imaginary part, out of the denominator so we can write this one fraction as a proper complex number with a real part and an imaginary part. We're going to multiply the numerator and denominator by negative 3 plus 4i. And carefully distributing, we've got 5 times negative 3 is negative 15. We have 5 times 4i, giving us positive 20i. Here we've got negative 2i times negative 3, giving us a plus 6i. And we have negative 2 times 4 is negative 8, and I times I is I squared. In the denominator, of course, we're multiplying a pair of conjugates. You can think about that factoring pattern for a difference of squares. A squared minus b squared is equal to a plus b times a minus b. So this is just going to be negative 3 times negative 3 is 9. We have negative 4 times positive 4 is negative 16 times I squared. The only two binomials that you can multiply together and not get a trinomial as an answer is this conjugate pair setup. Well, I to the negative, I'm thinking of the answer, I squared is equal to negative 1. And negative 8 times negative 1 is positive 8, and we have negative 15 plus 8 is going to give us negative 7. We got plus 26i. Oh, yay, the air conditioner turned off. And we have I squared is equal to negative 1, giving us 9 minus 16 times negative 1 will be 9 plus 16, which is 25. And now, with our denominator of this fraction being just a single, a real value, a real number, we can write this final answer as an improper complex number, which has got a real part. We have negative 7 over 25 plus 26 over 25i. Check my answer here, make sure that we are good to go. And we are. That is the end of our second example. Now, our third example, you're really going to have to lean heavily on the sort of cyclical pattern we have here with all of our powers of I, and either rely on that heavily and get to the answer, kind of efficiently, or identify what's going on with the numerator and denominator. So when I put this problem up here, maybe just pause the video and give yourself a challenge problem and see if you can't figure it out on your own before I reveal the solution. No. All right, let's see whether you got this right. If you happen to have stopped the lesson and tried this on your own, looks pretty challenging. Let's look at that cyclical pattern that we have here with our powers of I. Let's just look at it. If in the numerator of this fraction we're just adding a bunch of powers of I, then let's look what happens at the first four. We have I plus I squared plus I to the third plus I to the fourth, which is going to be the same as I to the fifth plus I to the sixth plus I to the seventh plus I to the eighth, which is going to be the same as I to the ninth plus I to the 10th plus I to the 11th plus I to the 12th, and yeah, okay. So I, well, great. I squared is negative 1. I to the third is I squared times I, so that's going to be negative I. I don't know why I'm doing plus minuses. And then finally, I to the fourth, well, that's equal to 1. Okay, so negative 1 plus 1 is 0, and I minus I is equal to 0. So in groups of 4, if you start with a power of 1, every 4 terms in sequence from I to the first is going to have a sum of 0. Well, if we could take all of those cycles of 4 out of this very long sequence of additions, maybe this actually just simply adds up to 0, or there's a couple of remaining terms outside of these cycles of 4 that we actually need to add. So let's go to our highest power. We have 1950, and divide that by 4. 4 times 4 is 16. Subtract, giving us 35. Let's see here. 4 times 8 is 32. Now we're going to have 30. We're going to have 4 times 7 is 28, giving us a remainder of 2. So we have 487 sort of groups of 4 terms added together, starting with I sub 1, I to the first power, I to the second, I to the third, I to the fourth, start over. It's really just the last 2 terms in this series of additions that we need to add up. So we have the numerator can be simplified to be I to the 950th power plus I to the 949th power. Now in the denominator, let's take a look at that. In the denominator, we have a bunch of factors being multiplied together. Well, again, with this being the same as or equivalent as I to the 5th, I to the 6th, I to the 7th, I to the 8th, whatever the first 4 multiply to, the next group of 4 is going to multiply to, and so on and so on. So let's look at the product now, since that's what's going on in the denominator, the product of the first 4 factors. So we have, with a different color, we have I times I to the second times I to the third times I to the fourth. Well, that's just going to be I times -1 times -I times 1. I times I is negative I squared. -1 times +1 is -1. I squared is negative 1, so we have negative 1 times negative 1. This final answer comes out to be negative 1. Now, I'll admit that the first time I did this problem, I tried to do too much of this in my head because I, kind of like live and breathe this stuff, and I wrote that the product was equal to 1. And thankfully, I did the question on with our second technique and caught my mistake, and I'm pausing for a bit on my notes because I partially corrected my notes that I'll use for my class. So every 4 factors, at least since we're starting with I to the first, every grouping of 4 factors is going to come out to be negative 1. So we have what? We've got 487 cycles of products which are equal to negative 1. So we have I to the 1950th power times I to the 1949th power. Looking at those last two because we do know that there's a remainder of 2 when you divide 1950 by 4. And we have what's left, we've got of negative 1, and negative 1 is being multiplied by itself 487 times. So we're looking at, this had a remainder of 2, so we're looking at I squared, because again I'm just using that fact that when we did 1950 divided by 4 we had a remainder of 2. So this is equivalent to I squared. Backing 1 off, this is going to be equivalent to I. And in the denominator we have negative 1 to an odd power is a negative 1 times, well, this again had that remainder of 2. So we're looking at times I squared. That means that we're looking at negative 1, and we have I squared is equal to negative 1. So we have I squared, which is negative 1, times negative 1, which is 1, times I. Okay, I'm super prone to mistakes, and I just wanted to make sure I didn't have any, and we're good to go. Now, we're going to rationalize this so that we can write it as a proper complex number. We're going to multiply the numerator and denominator by I. I keep saying rationalizing as if we're getting square roots out of the denominator, but we do want that I out of the denominator. That's going to give us I squared minus I over I times I, which is I squared, and I squared is equal to negative 1 minus I. Again, I squared is equal to negative 1, and we come up with 1 plus I. So this sum from I to the first times I to the second times I to the third, all the way up, keep adding till you get to I to the 1950th power over I to the first times I to the second, I to the third, times, up to multiplication of I to the 1950th power. That all just simply comes out to 1 plus I. Now, what if you did not rely on the cyclical pattern of this pattern repeating every 4 steps? And by the way, the reason why I pause so long is because I am really prone to making sign errors, saying 2 and 2 is 4 but write 5, and in my notes I did all this, but I did not pay attention to the fact that the product of these were equal to negative 1. Actually, I wrote that out, but I kind of just wrote this and had an I times I squared, forgetting that, yes, that is a product which is equal to negative 1 raised to a 487th power. So that basically we're multiplying by negative 1 itself 487 times, and I had a sign error in my notes. So while this was quick, and actually really the way you want to do this problem, there is another way of doing this particular question. And maybe you have these powers set up so that you're adding by 3 or 4 or 5, which you can handle. Like if this was I to the second, I to the fourth, I to the sixth, and so on and so on, you could maybe do some kind of factoring until you break it down to a point where your powers are increasing by 1. But let's just leave this the way it is and look at it in an alternative method. We have a partial sum in the numerator where each term is getting larger by a factor of I. This is a partial sum of a geometric series with an a sub 1 equal to I and an r value which is equal to I. You're multiplying by 1 to get every new term in this series of additions. So we can remember that the partial sum of a geometric series is a sub 1 times 1 minus r to the n power over 1 minus r. Well, our first term here is equal to I. We are constantly multiplying by I. And I don't have to do too much work to figure out that I'm going to start n at 1, because with your sequences in series, the domain of those functions are 1 to all positive integers starting at 1 and going up. So it's not too hard to figure out that we're just starting with 1 and counting by 1, that we're going to go up to basically where n is equal to 1950 over 1 minus r over 1 minus I. Well, I've already done the division, and I know that when we do 1950 and divide it by 4, that came out with a remainder of 2. So this is equivalent to I squared. I squared is equal to what? Negative 1. So we have 1 minus negative 1 over 1 minus I. So we're looking at 2I over 1 minus I. And that doesn't look anything like our old numerator of what? Negative 1 plus I. But that's because we need to get the I out of the denominator. So we're going to multiply by the conjugate, which is 1 plus I. That's going to give us 2I as we distribute, plus 2I squared over, and we have a difference of squares pattern here, we have 1 minus I squared, which of course is 1 minus negative 1 or 2. And here we also have another I squared, which we know now is equal to negative 1. So we're looking at negative 2 plus 2I over 2. Factoring the 2 out of the numerator and canceling, we have negative 1 plus I. The same numerator that we found when we took out all of those cycles of the addition of 4 terms. So there's more than one way to deal with this problem. Now, that's only the numerator though. And we've already done more work just to find the numerator, the sum, the partial sum here that we have in the numerator. And we haven't even gotten to the denominator yet. So this is clearly not the quickest way of doing this problem, but an alternative way. And hey, what's wrong with reviewing some other concepts? The more tools in your toolbox, the more options you have of solving problems. We're not just solving these by memorizing steps that limit how we do a particular problem. And God forbid we forget one of the steps, we're all completely lost. Now in the denominator we have a bunch of multiplications, and of course when you multiply like bases, all you do is add the exponents. So for the denominator, we have I raised to the 1 plus 2 plus 3 plus 4 plus 5 plus all the way up to 1950. Well, it might be pretty simple, but do you recognize that pattern? You have a partial sum of terms that are created by constantly not multiplying this time, but by constantly adding. Our exponent is a partial arithmetic sum. So our a sub 1 term is equal to 1, and our d is also equal to 1, because we're just adding by 1 to get the next term. And the partial sum for an arithmetic series is equal to s sub n, which is equal to n over 2 times a sub 1 plus a sub n. Well, again, we have a first term which is equal to 1, and we just are simply adding by 1. So again, it's not too complicated to figure out that n here is equal to 1950. So we're finding the partial sum of the first 1950 terms that's within our arithmetic series here. So we have 1950 divided by 2. A sub 1 is 1. A sub n is 1950. We're looking at, so whatever this comes out to times 1,951 comes out to the grand total, which is some massive number, 1,902,225. So maybe a little bit less care about, is it negative 1 to the 487th power and all that other good stuff. We get these like massive numbers, but we're going to be now reliant on a calculator, so very long hand calculations. But again, look in here that we have I to the 1,902,225th power. We can divide that by 4 and get 4, really the answer isn't important, it's what the remainder is, but it's 475,556, and yada yada yada. After all that math, you have a remainder which is equal to 1. Okay, so now we're looking at negative 1 plus I over I to the 4th raised to this huge number, which is going to be 1 anyway. Basically, it's just over I to the 1st. Now we're going to double check that I've copied this correctly. We're going to get our I out of the denominator by multiplying the numerator and denominator by I, wrap that up in parentheses, and we have negative I plus I squared over I squared. This is going to be, with I squared being negative 1, and actually so is the denominator, we have negative I minus 1 over negative 1, and we have t I plus 1, and which is the same answer as we had with our other technique. And that is the end of my last example. I'm Mr. Drew. Bam! Go do your homework.